Welcome, MHFers, to finally the last lesson on trigonometry, the last new lesson. It's actually 3.16. There's a typo there. 16 different lessons, feels like 1,000 videos and endless hours of listening to me talk about trig, but this is it. I wish I could say that it was going to be short and sweet today, but it ain't going to be short and sweet today. It's going to be a long haul probably, so strap yourself in. For the 3-minute review, I am going to go fairly quickly. I've got everything sort of written and I'm going to reveal, so do not be afraid. Hopefully you've already tried this, so you can just add to your own solutions. But don't be afraid to pause the video and take the notes that you need to. Something that we talked about perhaps when we got going on identities, and not much since, is the difference between an identity and an equation. And hopefully you've kind of got a feeling, but here's some things that you might have said. Um, an identity, we work with the left side and the right side separately, right? We're not allowed to work with it as an equation because that would be assuming that the identity is true. And we can't do that. We want to work with the left side and the right side separately, where in an equation, we can move stuff from side to side because we know that it's true, and we're actually after the variables where it's true. Another thing that you might have said, what we do with an identity is we prove it. What we do with an equation is we solve it, right? And what that means are these things, and maybe this is the most important point. When we're proving an identity, we know that it's true for all values of the variables, at least where the functions are defined, right? Because sometimes there's holes in the left side and the right side where the left side and the right side isn't defined at all. Things like tan x and cosecant x and stuff like that aren't always defined, but for all other values where they are defined, it's an identity. Whereas an equation, what we're up to is we're asked to find values of the variable that make the equation true. Identity, it's always true. Equation, we're asked to find the values where it's true. That's what solving means. Dandy. All right, so if we're asked to identify whether a given equation is also an identity, or in this case we're given two equations, we have to figure out which one's the identity and which one's the equation, prove the identity and solve the equation. That's kind of tough. Although we might have some instincts about what one looks like an identity now or an equation, but what might we try? Maybe you'd try and test some values. Remember, the idea is the identity holds for all values. So you pick a value. Pick, say, x equals pi over 4. And I just picked that because, when I picked 0, one of these was undefined, and that's not going to help me if it's undefined. So I picked pi over 4, and I was checking things out. And so for this one, the left side, when I checked it out, the left side, and I did some work, exact angles, all that business, it worked out that both the left side and the right side, it's true. So what does this tell me? It means it's true for x equals pi over 4, but does that tell me that this is the equation or the identity? It does not. It doesn't tell me one way or the other. It maybe gives me a hint that it's an identity, because what's the chances that I lucked on to the solutions to an equation? There might be only one or two solutions to an equation, and chances of me just guessing it are pretty low. So this might be the identity we're thinking. But when we try pi over 4 over here, when I try it, the left side is not equal to the right side. And that's an important calculation, because as soon as I find something that doesn't work, as soon as I find a value of the variable where it doesn't work, remember that's called a counterexample, and I know that it's not an identity, right? It's not an identity. So this must be an equation that I can solve, even though we haven't seen anything like this yet. And this is actually today's stuff. So one way of deciding is to try test values. Another way, and we saw this last class, or maybe 2 classes ago, I can't remember now, that we could pull out a calculator, graph the left side, graph the right side, when y equals the left side and y equals the right side, and check it out. So here I did that. I want to here's the left one. You see 1 plus 1 over tan x squared and 1 over. Remember, there's no cosecant button on the calculator. So for cosecant x, I had to put in 1 over sine squared x. But again, that 2's got to go on the end. So I graphed that, and look, a complete match, a complete copy. And in fact, I took a screenshot while this second bold one was coming in, and I can see that this indeed is the identity because it's true for all variables, or at least it looks like it. That would give us a hint, strong evidence that probably this one's the identity. Where over here, when I graph the left side and the right side, and notice that, you know, these are things that you should have been able to graph. I could, you know, you could have done a sketch of this and known that, well, the period of this side is different than the period of this side, so chances are there are only a few solutions and that this is the equation. In fact, it looks like where the bold one is equal to the thin one here, there might be 1, 2, 3, and remember, this is where this is principal solutions. It looks like there might be 2 solutions, and maybe that's it. Maybe more. I don't know. There might be another one in here, although it's kind of hard to see when with the graphing calculator. It's not too precise as far as the graph is concerned. Desmos might give you more accurate answers, although it looks like this is something we might be able to solve perfectly, this square root of 3. So how would we do it? And again, pause if you need to. This is old, right? This is old. So, and in fact, this is one of our Pythagorean identities. Maybe you recognize it. Identity. We didn't prove this one, but this is one of the Pythagorean identities. But I did the left side and right side, wrote everything in terms of sines and coses, common denominator, everything worked out great. This is actually an easy one. You want to hope for that one on the test, although I can guarantee you that one won't be on. Probably that this is a fact that we might use. So old. This is old and no big whoop. The equation is something nasty. I mean, we're used to seeing only like this part equals something. You know, even the sine 2x, you know, we saw this was kind of a, where we said theta equals 2x. That was kind of hard, but now we've got a mixture of 2 pieces. And we just got going on this last day, and hopefully you had some success. But what was one of the skills is factoring, but I can't even factor this. This is today's stuff, okay? So you're going to see really quick a version of, maybe this is one of the harder ones that we would even do after today's class. So if I'm going fast in here, be patient, because this is what we're talking about today. Today's lesson will build up your tolerance for C. And I'm dinging, something's dinging here. I'm just going to have to close all those. Somebody's trying to send me an email or something. I wish they would just leave me alone. Let me finish my video. All right, so a strategy that we'll see is that, you know, I'd like to factor, but I can't deal with this sine 2x. I need to use an identity. And so I can pull out this, put in the left side, and see, now I've got a factor. I've got a common factor. I can't cancel, but I can factor. If I put everything on the one side, I've got a common factor. All right, see, common factor of cos x. I pull out the cos x, and what am I left with? I'm left with 2 sine x minus square root of 3, and I realize this might be going fast, but again, remember, this is today's lesson, and you're kind of absorbing this. All right, this gives me 2 separate equations. This is the idea of a quadratic trig equations. There's solutions here and a bracket here that gives me solutions. 2 equations wrapped into one, bracket and bracket. Over on this side, when is cos x 0? Cos x is 0, remember, where the x coordinate is equal to 0. This is the line x equals 0, and I used both the rotation angles and unit circle to do that. And I also said, hey, I could have found this on the graph of cos x. I can find the principal solutions, pi over 2 and 3 pi over 2. So there's the 2 solutions between 0 and 360 that I get from this first one. And the second one, well, that's not so bad. This part we solved early as well, right? I put the square root of 3 on the other side and divide by 2. It's a perfect angle, and I can see the related acute angle from my chart is pi over 3, and I get two solutions, x1 and x2, and off to the races we go. You said, well, Mr. Resta, why don't you do the plus 2 pi n business? Well, remember the plus 2 pi n business came in handy if there was something odd going in with the x, like a 2x or a 3x or an x plus pi over 3 when I needed to do something in there. This one is actually a grade 11 equation, straightforward, and then I can get the rest of the solutions. It's actually not that bad. So what's the moral of this story? This quadratic trig equation, well, there are some strategies in here that we can use, some tools, some trig tools to use that splits a hard, very difficult looking equation into things that we're more familiar with. Depending on the time, I'll pick up the lesson. Yeah, I'm going to pick up the lesson in part 2. I'm guessing this is going to be a 3-parter though, folks. So I'll pick it up in part 2.